We present a suite of enhancement techniques for visualizing earthquake seismic waves. Here, we show a bridge foundation ground model which was developed based on the structural configuration and local soil conditions of the Humboldt Bay Middle Channel Bridge in Eureka, California. Scientists from UC San Diego used this model in their earthquake simulations, generating a dataset containing three-dimensional displacements for each node to represent the movements caused by the earthquake's seismic waves. The overall displacement can be decomposed into two main motions, drifting and shaking. Drift is a permanent deformation which is usually contained within the low frequency band and is the product of slumping, settlement, and/or heaving of the system. Shaking is the cyclic motion of seismic displacements contained in the high frequency band, seen as back and forth movement. Here we show the dataset using traditional wireframe-based rendering. The colors represent the magnitude of the node displacements. However, it is difficult to see the underground motions as the inner portions of the mesh are occluded by the outside. People have also rendered seismic data using direct volume rendering, but without separating the high and low frequency bands, we are not able to distinguish different seismic waves within the data. Also, since the dynamic shaking motions are superimposed with accumulated drift values, it is difficult to distinguish their different contributions. To provide an intuitive visualization of the simulation, we first perform seismic analysis on the displacement fields to extract the intertwined motions. In this animation, we show the low-pass vertical and the high-pass horizontal components of the displacements using different transfer functions. We can see that as the shaking continues, the bridge ramps sink. However, even with the different transfer functions, it is still difficult to get a sense of the high-pass back and forth motions using volume rendering. Instead, we propose using deformable, implicit surfaces to display the high-pass band. Here the surfaces are superimposed with the low-pass parts displayed using volume rendering. In this animation, we have a much clearer view of the low-pass band while providing an intuitive display of the back and forth motions contained within the high-pass band. Our suite also provides other common techniques that scientists find useful for their analysis, such as using extra geometry to render portions of their dataset. Here we focus on a bridge pier and superstructure on the southeast side. In this example, the scientists were interested in how the bridge piles deformed as the bridge shook during the earthquake. Our framework for visualizing earthquake seismic data consists of several parts: frequency decomposition, resampling, direct volume rendering, and deformable, implicit surfaces. With our techniques, different frequency components may be visualized together or individually. This allows scientists to better comprehend and observe the complex, previously hidden spatial and temporal relationships between the components. We believe that our system provides a novel way for scientists to interactively investigate and explore their seismic data. With our techniques, scientists can quickly gain valuable insight into their simulations. It is our hope that our system will aid the development of new methods for protecting real-world infrastructures against otherwise devastating earthquakes.